All right, so we're going to connect this 68681 Uart to our homebrew computer today. So before we start soldering, I just want to go over what the hell that means, okay? So the 68681 it's a UART, right? And the UART stands for Universal Asynchronous Receiver Transmitter. It's a lot to digest, but basically what it is it's a device that allows us to send information back and forth between the homebrew computer and the PC, okay? So old school, they used to call this thing a serial port. You can call it a serial port too, okay? So basically what this thing's going to do, right, is I can just draw kind of a little picture of our board here real quick. So we got our microprocessor, we got our flash chip, we got our RAM chip, okay? And we're going to add this extra chip here, which is our 68681 UART, okay? And this is going to be connected basically to our address bus and data bus the same way as the flash and RAM is, okay? So we got an address bus that goes over to these guys. We have a data bus that also is going over. We're going to connect the 68681 in the same way, okay? So what's going to happen, so basically this 68681 is going to look like memory to the microprocessor, right? So if you remember the flash, here, let me label this real quick here, right? So we got our flash and our RAM. All right, and so the flash is addressable from addresses 0 up to, I believe it was 7F. Okay, and our RAM is addressable from addresses 80000 up to 17FFF. Is that right? That's right, I think. Yeah, okay. So we had done this using an address decoder, right? So we look at address pins A19, A20, and A21, and we determine what those address pins have on them, and if they have 000, then we're going to select the flash. If they have 001, then we're going to select the RAM, and so on. Okay, we're going to do the same thing with the 68681. Okay, so this is going to be addressable from 180000 up to I think it's 20. Let's see here. I guess it'll be 27 F, something like that, okay? So, obviously the 686, maybe not so obviously, but the 68681 only has, I can't remember exactly how many registers. I think it's 8 registers on it, okay? So we don't need this whole address space here. We're only going to need 8 addresses to talk to the 68681, okay? But we're just going to use, but we're dividing the address spaces up into these evenly divided regions of memory. So we will use the whole region of memory here. So basically the way this is going to work is we have this 74,138. We are taking addresses A19, A20, and A21 into it, right? And then that we have one select line going to the flash, we have one select line going to the RAM, and then we have the third select line is going to go to our 68681, right? Okay, and so that's how we're going to read and write data from this guy, okay? So on board this thing, we have a bunch of stuff, right? So the most important output pins that we have on board this guy are going to be our transmit and receive, transmit and receive lines, okay? So the transmit line is going to take the input data that we're sending to this thing, and it is going to serialize it. Okay, so we have when we send data, when we write data on the address bus to this thing, it's going to be written in parallel, 8 bits at a time over the memory bus. Okay, so the 68681's job is going to be to take that data and send it 1 bit at a time over the transmit line. Okay, and it will also take data that's received in serial fashion over the receive line, and it will make that data available on our microprocessor's memory bus so that we can read it. Okay, and so this is how we're going to communicate with a PC, right? The PC is going to send characters. So this is going to all go over here to a PC. Okay, so a PC is going to send bytes over the receive line, which can be decoded by the 68681 and then read by our microprocessor, and then we can send bytes over the transmit line the same way. Okay, so how do we actually do that, right? So what we need to do is the PC and the homebrew computer need to agree on a speed at which to send them. Okay, so they need to agree that every bit is going to be sent, is going to take a certain amount of time to send. Okay, and so on this one we're going to use 19,200 bits per second. Okay, so this is we call this 19.2 kilobaud. Okay, so that means that 1 bit time is going to be 1 over 19,200, and this is in seconds. Okay, so we're going to be sending a data at about roughly 20 kilohertz. Okay, on our serial bus, on our transmit and receive lines. Okay, so with both the transmitter and the receiver, the homebrew computer and the PC are going to agree, we're going to program this data rate into our UARTs for both of these guys, and they're going to send data back and forth. So they're going to serialize characters, right? So the way it's going to work, let's say we want to send the character 0. Okay, this is the digit 0. Okay, so in ASCII, you can look it up. If you just go to ASCIItable.com, you can look up what the ASCII representation of this thing is, and I happen to know that it is hex 48. Okay, so what we're gonna end up doing is we're gonna send the number hex 48. Okay, so our microprocessor is gonna write the number hex 48 over the data bus. It's gonna write that number into our 68681 UART, and then our 68681 is just gonna serialize it. Okay, so what it's gonna do is in order to serialize it, it can't just send the data bits in the raw. Okay. So what it's going to do is it's actually going to add 2 extra bits, right? 1 start bit to tell the PC, hey, I'm about to start sending data. Okay, so first it sends a start bit. Okay, and then it's going to send the serial data of hex 48. We'll talk about how that happens in a second. And then finally, it's going to send a stop bit, which indicates to the receiver that we're done transmitting. Okay? So basically we serialize the data, but we are sort of like putting these extra bits on the beginning and the end sort of as a handshake to make sure that the receiver can receive them correctly. Okay, so here's what that actually looks like, right? So we have time on the x-axis here, and I believe the bus, when it's inactive, it starts out high at 5 volts. Okay, so as soon as we want to start sending data, what we're going to do is we are going to start with our start bit. Okay, and this is going to be 1 bit time long. Okay, so 1 bit time is 1 over 19.2 kilobaud. Okay, so we're going to start with our start bit. And then we're going to start serializing our data, okay? Okay, so we can start, I can't remember if it starts with the least significant bit or the most significant bit. Let's say it starts with the least significant bit, okay? So let's translate this serial data hex 48 into binary, right? So in binary, it's going to be 0, 1, 0, 0, 1, 0, 0, 0. This is the bits that it's going to send, okay? So we'll say it starts sending a 0 first, which is the least significant bit, okay? So when we send a 0, that's going to be 0 volts on the bus, okay? There's my 0. Okay, then we're going to send our second 0 here. And then we're going to send our third 0. And then we're going to send this 1. but we don't want, so in order to send the 1, we need to change the voltage to 5 volts. So there's the 1. Okay. And then we're going to send another 0. Okay, so we need to change the voltage back down to 0 volts and hold it there for 1 bit time. And then another 0. And then another 1. And then another 0. And then once we've done that, then we're going to send a stop bit, which I believe is a 0. Okay, I shouldn't write it as a 0. I should write it as a stop bit. And then the line becomes inactive again. So this is how we serialize our data over the serial bus, right? So we have 8 data bits here that we want to send, okay? 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, that's a character hex 48. But because we have to append the start bit and the stop bit on the beginning and the end, then we actually end up sending a total of 10 bits, okay? So we have 8 payload bits, but in order to send the 8 data bits, we have to actually spend 10 bit times sending them, okay? So there's this overhead of adding the start bit and the stop bit that we have to set up, okay? And you can configure these serial ports differently, right? You can send 2 stop bits instead of 1 stop bit. You can also configure it to add an extra parity bit at the end. I believe it's between the last data bit and the stop bit. Okay. So depending on how you configure your UART, you can add extra stop bits or parity bits or start bits or whatever. This is the most common configuration, right? So it's 8 data bits, 1 stop bit, and no parity. That's typically how we set this thing up. Okay, it minimizes the amount of overhead that we have to send. Okay, because if you have to send a parity bit too, then of course now we're sending a total of 11 bits just to get 1 byte across the line. Okay, 1 byte of actual payload, right? So this is preferable. Okay. Anyway, so this is how we transmit data 1 character at a time. Okay, so if we want to send multiple characters, then we just keep doing this over and over. We send the start bit, we send all the data bits, and then we send the stop bit. And then we send the next character by sending a start bit, data bit, stop bit. Okay? We can't amortize the start bit and the stop bit over multiple characters. Okay? Okay, so when we hook up this 68681, because we need this special bit right here, this 19.2 kilobaud, right? We need to have a special clock too, okay? So this 68681 is going to have its own clock that's independent of the microprocessor's clock, right? So the microprocessor is running at, let's say, 12 megahertz, okay? But the 68681 has its own clock, which is clocked so to make it run at 19.2 kilobaud. Okay, so we can change the speed of the processor. We can increase or decrease the 12 megahertz clock on the processor, and that won't affect the speed that we're transmitting on the serial port. Okay, so we're actually going to use I think it's a 1.8 something megahertz clock on our serial port here. Okay, so it's actually, the clock is a lot faster than the speed of the UART, and internally that clock is going to get divided down to 19.2 kilobaud. Okay, so the nice thing about that is that it allows us to select different baud rates, right? So if we want to change the baud rate, we just change how much we're dividing our input clock, and we can basically change the speed of our serial port, right? I think there's another UART called the 6850, which could also be used with this processor, but that one has a fixed clock, right? So you have to give it can't remember exactly what it is. I think you give it a clock that's 16 times as fast as the baud rate that you want to transmit at, and that's it. There's no option for having a variable amount of division of your clock rate. So you're basically, your hardware fixes the speed at which you can transmit data across your serial port. Okay. So anyway, so modern processors and microcontrollers also have these serial ports. Like the Raspberry Pi has 2 serial ports on it. The main difference between the Raspberry Pi serial port and the 68000 serial port is that the 68000 has a completely separate chip that implements the serial port, right? Whereas the Raspberry Pi, it's all integrated on the main microprocessor, right? So that's the main difference. But there's still basically people are still using these things today to send information because it's very reliable and very simple. Okay. So there's quite a bit of programming that you have to do to set this thing up. It's not just kind of set and forget. You can't just write some data word to the 68681 and have it get transmitted. There's some setup that you have to do to make it work. We'll go over how to do that setup after we get the thing soldered up. But let's start out by soldering our chip onto our board and getting it running. All right, this is kind of an odd socket because it doesn't have a U on one side. It's both of the sides are kind of flat. So I'm just gonna say this one has a little bit of a notch on the top here, so I'll have to call that the U. So we'll put that on the pin 1 side here. Just anchor it to the board. Okay, and then we got our clock here. So the input to the clock is going to be on pin 32. It's going to be right here. So we can put our clock right next to it there, I think. It's a good spot for it. I'm gonna move it over just a hair. This is going to be a lower frequency clock than the microprocessor clock. All right. Okay, so that's gonna work. So let's set up some decoupling caps here as usual. I'm gonna put my decoupling cap right here on this ground bus here, so I only have to solder one wire to it. Oops. Trying to cram this thick 26 gauge wire into this hole here. I've been complaining about that the whole time I've been building this board because it doesn't work. It's not working for me. Okay. Here's my 5-volt power for my clock. At least that one should be easy to get at. Okay, so I had to go and I had decided to just finish soldering the 68681 off camera. And what I ended up doing here is, let me just take you through it. So this is the back side. We got the address lines going to the 68681. We got the data lines going over there. We got the clock, right? There's a clock signal here. And then I also connected a chip select pin from our 74138 address decoder. And that's going over to the chip select pin on the Uart here. Okay. So that works. The one little problem we end up having with this device is that the 68681 is significantly slower than the memory, right? So for example, the memory that I spec'd out for this board, I think both of these chips respond in 55 nanoseconds, which is less than the period of one clock cycle. At I think 12 megahertz or something like that, right? A clock cycle at 10 megahertz is like 100 nanoseconds. So 55 nanosecond memory is almost up to 20 megahertz, right? So these are very fast devices, and and they can respond in less than a clock cycle. So it's okay for us to wire previously when we just had the memory on our bus here, we had just wired the DTAC signal directly up to address strobe because because the memory was able to respond right away. Okay. But the 68681 is slow, right? It takes 175 nanoseconds, so more than 3 times as long to respond to a data input, right, or output. So that's not good, right? So we can't just wire address strobe directly up to DTAC if we want to talk to this to the 68681. I tried it, I thought maybe I might get lucky and it might work, but it didn't work. So anyway, I had to come up with a different way. Okay. So the alternative that I came up with is basically I'm going to use a multiplexer to choose the input to the DTAC on the processor, right? And the way that's going to work is basically one input of the multiplexer is hooked up to address strobe, the way we had it hooked up before, okay? And so if we're talking to memory, so if the memory is going to be selected, then we're just going to route address strobe over the DTAC signal, okay? And the other input of the multiplexer is going to be hooked up to the DTAC, which is coming from our 68681, right? So the 68681 actually generates its own DTAC signal. And then what I'm doing is I'm taking that DTAC signal from the 68681, I'm routing it over to this multiplexer, and depending on which chip is selected, if this guy's being selected, then the multiplexer is going to route the DTAC signal from the 68681 over to the DTAC signal to the processor. If the memory is being selected, then we're going to route the address strobe from the processor to the DTAC of the processor. Okay, so that's how we're going to solve that problem. It's a pretty straightforward solution. Okay, and I think that was the only weird thing that I had to do to this thing to get it to work, to this UART to get it to work. So, I fired this thing up. I wrote a couple of little test programs for it in Easy68K, and things weren't working exactly correct. So I had to debug a little bit. And what ended up happening, I ended up that there were a couple of little problems that I needed to solve, right? So the first problem was related to the way that we're converting an S record generated by Easy68K to a binary file using EasyBin, right? So EasyBin, when you load a new S record, it doesn't just replace the contents of its buffer with the new S record, right? What it does is it overwrites the byte by byte. It overwrites the contents of its buffer. Okay. The problem is that if we have some old stale data in there from a previous S record that we had previously converted, all of that stays in there unless it gets overwritten by the new data from the new S record, okay? So what you need to do is you need to manually clear the contents of the buffer in EasyBin in order to make sure that you get a fresh buffer every time you need to convert an S record, right? And so that was giving me problems, and my programs weren't running correctly because I had some stale leftover data in there from a previous program. Okay. And another, let's see here. Yeah, okay. And then the second problem that I had was, I believe it was on the RAM chip. I had accidentally swapped the read-write not pin and A17. And that was causing writes to fail when writes to RAM were not working, right? And so, so every time I would try and store the value of a variable, or if I would try and call a subroutine, it just wasn't working, right? So I basically what I did is I figured out that that it wasn't working because I wrote a couple of test programs to test to see if writes to memory were working, and they weren't. So I just went and I traced all of the connections on the address bus out to. I think I used this was a couple of days ago, so I can't remember exactly what I did. But basically, I just used this digital multimeter here to trace all of the connections from the 68K over to both memory chips. Okay, and the way I tested that is I actually wrote a program that would write a value to memory, write a value to SRAM, right? And then read that value back from SRAM and compare it to the original value that had been written. Okay, and if they weren't the same, then what I did is I wrote to an address that is not mapped on this board. Okay, so it's an address above the base address for the UART. And what that did is it caused one of the chip select pins on my 138 address decoder to be asserted. Okay, so I kind of used those as indicator outputs. I used the chip select pins as indicator outputs to tell me if certain conditions were happening in the program. Because the problem was I didn't have a functioning UART, so I couldn't print anything out to the terminal, and there was really no other I/O available to me, right? So I had to come up with some way to generate some kind of a signal in my program that would indicate to me whether, when certain conditions were happening. And basically the way that I did that was I just wrote to different addresses in the memory space, which caused different ones of these chip select pins to be asserted based on different conditions. And that's how I figured out that memory wasn't working, right? And then I fixed the problem. Okay, so so I mean, I probably should have traced every single one of the wires from the processor over the memory, and frankly, I'm kind of surprised that I didn't have any more problems than I had. I think, as far as I know, I only had one swapped wire, so I got extremely lucky on that, right? Yeah. Okay, and then the last problem that I had was that I screwed up the circuit that generates the write enable signal to the RAM, right? And that was another reason why my writes to memory weren't working, right? So I originally had wired the read write not pin from the processor directly up to the memory chip, to the SRAM chip, okay? But it turns out you need to wire them up. You need to wire it up through an OR gate, okay? So you need to OR read write not with address strobe. And that becomes the write enable signal to your RAM. Okay, and I hadn't done that correctly. So I've corrected that on the schematic now. So you should be able to go on there and see what the final version looks like. Okay. So anyway, I tested this thing a little bit with a couple of programs. I wrote a couple programs in Easy 68K. One to blink this LED on here. I set this LED up to be connected to one of the output ports on my 68681, and I'm able to blink the LED, and I'm able to write stuff to the output port. Okay, I'm able to write stuff to the UART. Right, so I can read and write from the UART. Interrupts appear to be working, and so everything seems to be good. So then what I did, the next thing I did was I downloaded the GCC C compiler that targets the 68,000 instead of the usually GCC is just targeted for whatever machine that it runs on, but this is a cross compiler. You can get it from Ubuntu, and it'll generate output code for the 68,000. So we'll talk a little bit about how to actually use that thing to write programs, so you don't have to write every single program in assembly language.